Thank you, Sarah, for such a kind introduction. I would like also to thank ACDLabs for the invitation and Dimitris, who just gave such a wonderful talk for this invitation. And I'm really impressed by the how the ability of the ACDLabs software to handle the measurement of RDCs and fitting the NMR, the RDC data to structures. Well, let's move on with my talk. First, what I would like to say is that let's assume that we already have a constitution, molecular constitution, produced by the ACD software, by the structure elucidator. And then now we need to determine the relative configuration. And I would like to mention about the limitations of NOE and J coupling constants analysis. For example, if we want to determine the relative configuration of carbon-3 and carbon-17 that are located 8.7 angstroms away, what I do is I just go through a relay of J coupling constants or NOEs, and in that way I can correlate because I have it in a certain way a spatial information. But if we introduce a linker and then we separate these both sides of the molecule, and now, for example, this proton and this proton is 7.5 angstroms away, we break the relay of J coupling constants, and also we break the NOE interactions, and which normally the limitation is 4 to 5 angstroms. So to overcome this limitation, we need an NMR parameter that provides information of non-local character, because that information that is provided by J coupling constants and an NOE is of local character, only the closed environment. And the answer is dipolar coupling. The dipolar coupling is a direct interaction between the magnetic moments of a couple of spins, I and J, and here you have what they add, and then when the interaction is a negative, and this one is a positive, though they sum and they subtract, and that interaction can be between any magnetically active nucleus, for example, proton-proton, proton-nitrogen, proton-carbon, carbon-phosphorus, carbon-fluorine, and they can be bonded or non-bonded. And that interaction depends on the product of the gammas, the gamma I and the gamma J, and depends also on 1 over to the distance between them and to the cube. And the most important part is that also depends on this angle between the internuclear vector and the magnetic field. If there is a J involved in the interaction here, then this splitting is gonna change into a total coupling, that is J, that is the scalar coupling, plus D, that is the dipolar coupling. Looking at this equation, you can see that D provides extremely powerful structural information of non-local character due to its dependence with the distance between the internuclear vectors and the angle. And if we have a unique combination of dipolarly coupled pairs of spins, they can produce a unique set of dipolar couplings that in turn can lead to the unambiguous determination of the relative spatial arrangement of all the atoms in the molecule. This spatial arrangement reflects the constitution, the configuration, and the preferred conformation or conformation of the molecule. Well, when it comes to configuration, we have to say that NMR cannot distinguish absolute configuration. So when we talk here about configuration, we are referring to relative configuration. Well, explaining the concept in this way, the use of dipolar couplings to the analysis of small molecules sounds very simple and straightforward. However, dipolar couplings are in the order of kilohertz. In solid state powders, all possible spatial orientation adopted by molecules lead to extremely broad NMR lines, making the extraction of individual dipolar couplings very difficult or nearly impossible. On the other side, when we go into solution, they average out due to the isotropic molecular tumbling, and they are not observable in the NMR space. They're invisible. But, okay, so if we force molecules to adopt a minor degree of alignment in solution and no longer tumble isotropically, a measurable fraction of the dipolar coupling, 10 to the negative 3, 10 to the negative 4, can be observed in the NMR spectrum. This fraction is known as the GDO, the global degree of alignment, and is a property of the alignment and also of the size of the molecule. This fraction of the dipolar coupling is called residual dipolar coupling because it's the residual value of the original dipolar coupling. What is interesting here is that RDCs maintain the same angular information as the original dipolar coupling. We don't need the original dipolar coupling. It's just with having a fraction, we can get the same information. And the most important thing is that this information is of non-local character. That is the information that we need. And RDC's value depends not only on the internuclear distance between them, but also on the angles of the internuclear vector with respect to the internal magnetic field. Hence, RDCs provide information about the relative orientation between these internuclear vectors, but regardless of the distance between them. That's the beauty of RDC. So these internuclear vectors can be 1 angstrom, 10, 20, 40, 50, 100 angstroms away, because if you look at the equation do not encode for the distance. We can't get the distance between them, but we can get the relative orientation. So since we already know the constitution and we know how the atoms are connected, well, the only thing that we need is to know the relative orientation of the internuclear vector. Well, experimentally, how we manipulate, this orientation at molecular level. We need to be creative, and that's what the pioneers on this did. And then if you expose the molecules to organize or align columns in solution, like the lyotropic liquid crystalline phase, or you expose them to cavities, you will create certain order, because when they are in isotropic solution, they adopt all the possible orientation in solution, tumbling fast, and then that is why the RDCs average out and is 0. But if you use a stretched polymer gel or a compressed polymer gel, or you use these helical polymers, and there is other stuff like graphene oxides and self-assembly peptides, that is how we do it. So aligning small molecules, as we can use, as I said, we can use compressed or stretch aligning gels. High quality gels for compression and chloroform and DMSO are commercially available. Contact me for more information. They can also be made according to published recipes in the literature, but let me tell you, the quality of the gels that are provided and are commercially available are very high quality, they are very clean, they don't contain monomers. On the other side, we have this lyotropic liquid crystalline solution in organic solvents, and the most popular, because it's commercially available, is the PBLG. You can get it from Milliport Sigma for $600 a gram, and you can make 10 samples probably with this. And also you can get polyacetylenes that are commercially available from this company, Carbolution. Here is the link. And then the price and literature information about these phases is available in the product page. But Carbolution is in German. Yeah, there are many other LLCs proposed for an isotropic NMR analysis, but they are not commercially available, Joe. Sorry, yet. such as PELG, PCBLL, polyguanidine, and recently the graphic graphene oxides and the self-assembled oligopeptides. So to be realistic, the goal here is, okay, so you want to collect RDC, okay, I'm gonna show you the practical aspect, and the practical aspect is, okay, what do you have available and how can we do it? And before moving on that part of the talk, let me just stop here and talk about another important anisotropic NMR parameter that is called the quadrupolar coupling. The quadrupolar coupling is observed in a quadrupolar nucleus or nuclei that have a spin I larger than 1/2, because 1/2 are very spherical. And when these quadrupolar moments, they interact with the electric field gradient, that is a tensor in the molecule, then the energy levels change, and also it's anisotropic because depends on the cosine square of the angle, and these levels, you know, that are equal in isotropic solution. No, it's not an isotropic solution. Sorry. When you have this interaction with the electric field gradient, you know, this interaction oscillates depending on the orientation, and also average out in isotropic solution. But again, when it is exposed to an alignment medium, then you see a fraction, that this fraction is the residual quadrupolar coupling, because the quadrupolar coupling is very large as the dipolar coupling. And this fraction is what we normally use to check the sample. Here is just the deuterium quadrupolar, the deuterium spectrum with the quadrupolar coupling of the solvent in chloroform in a gel. I will show you more now in the next slide. So we use this. We normally, when we have the sample and we think the sample is anisotropic, so we use a 1D deuterium NMR spectrum of the deuterated solvent peak to verify first if the sample is anisotropic. If you don't see that splitting, your sample is not anisotropic. There is no way that you can measure residual dipolar coupling. Also, you will see the degree of anisotropy by looking at the value of the solvent signal splitting. Well, each solvent has different solvent have different electric field gradients. So for the same degree of alignment, you will not see the same split. And also the quality of the anisotropy by looking at the shape of the solvent. For example, here, this is a very high quality gel. This is a PMMA gel with a quadrupolar splitting of 50 Hertz. And then you can see here the splitting of the signal inside the gel when the gel is compressed, we'll see, and this one is outside the gel. Or if you make a lyotropic liquid crystalline solution of PBLG, here are 100 milligrams of PBLG in 400 microliters of chloroform in a 5 millimeter NMR tube, but the quadrupolar coupling of this is about 600 Hertz. So these one are in the order of 10 to the negative 3. In degree on GDO, as I mentioned, these one are in the order of 10 to the negative 4. But to be realistic, the alignment is so strong that we prefer to have a weaker alignment to measure RDCs, because in the way we measure them, we want to see them in values that are smaller than the J coupling. And these are really now very, very valuable alignment medium for residual chemical shift anisotropy, which is not the topic of this presentation. So I would be biased here. I've been working for probably, since 2007. My first paper was in 2008, on the development of something that people can use. So the idea is to develop a methodology that I hope it become more mainstream. And in 2010, we proposed this compression method in which we use a plunger, and then we were swelling a gel, and then we compress or relax the gel, as you can see here, and then you get cavities, for compression, and then here, this one, you can tell this is isotropic. This led to the development of a device for really precise control of the degree of alignment. The device is commercially available from New Era Enterprise, and we work with Frank Bosco on the development. So you can see it's a Teflon plunger with a lock and special NMR tube, as you can see here. And with this plunger, you can really change you have a variable degree of alignment at the user's whim. You relax it, you don't see alignment, you see isotropic spectrum. So you compress it, and then depending on the degree of compression, you can see different degree of alignment, and you can judge that by the splitting of the deuterium NMR spectrum. The other advantage is that compared to using lyotropic liquid phases, where you have to purify the sample, the gel is in the tube, you just finish your experiment, you can put it in the refrigerator, or you can just recover the sample. And then I've been told by colleagues that they told me, that also the beauty of these gels is that you can really recover the sample. I'm talking about milligram levels. I personally did it in my lab. Here you have the relaxed deuterium spectrum of PMSO. Here is compressed 4 Hertz, and here is a PMMA in chloroform. So here is the isotropic solvent, as I said, outside. And then here is the split in 34, but we have gels that can go up to 50 Hertz. At the same time, what we realize is that since there is always a residual part of solvent that is outside the gel, when the gel buckles when you compress it, then we discovered that you get J, and then you get T, you get the total splitting in a single experiment, and then this allows you to measure in a single experiment. You measure the J, and you measure the total coupling, and you get the RDC. The most common RDCs in small molecules, honestly, and to be realistic here, is the one bond proton coupling, because it's easy to measure. You can measure long range. I have papers on that. And another one that it can be measured is the 2 bonds, the geminal proton-proton. And these ones are, in order to measure with the desired accuracy, are very challenging, and they are very small. They are 1 order of magnitude. And most of the problems in which RDCs were used were solved using 1 bond proton carbon RDC. Our preferred pulse sequence to measure 1 bond RDCs is the Bird filter F1 couple J scale HSQC. You measure them in F1. So here you have an overlapping of the isotropic and the anisotropic. So you have here the total coupling, then you have here the J, and for CH2 you have the sum of the couplings, and then I will show you also for CH3 what do you see. But this is how we do it, and also we use the Bird filter, so we see only the 1 bond, and also we use pure shift, so we can measure them very accurately. Here is an example. This is the isotropic spectrum of strychnine inside a gel using outside the gel. So it's in isotropic solution. And you can see the splitting. This one is the folded aromatic peak. You see all the splitting in F1 and with a scaling of 4. And then here is in the gel, and then you can see inside and outside, so you can see both signals here. And if you ask me, I can provide the PAS program that runs in Bruker. With Theo Parella, then we developed the multi-purpose HSQC, in which we added the ability of scaling the chemical shift. And by scaling the chemical shift, we can use 0 chemical shift, and then we can run the experiment, for example, for artemisinin here, with no chemical shift in F1. And then if you have the signal very well resolved, these splittings are the J's or the T. But as I told you, here are the methyl groups. So if I make an expansion here, you get inside, outside, and you can directly measure the dipolar coupling, the residual dipolar coupling from the experiment. Here are for the CHs, H5, H11, H7. You can look at the paper. So these also we can measure for the CH2, for the methylene groups. And if you get overlapping, well, go to the one with chemical shift evolution in F1. And then here again, you will get a chemical shift. You will separate by chemical shift. You get the total coupling inside, the J coupling outside, and you can measure the RDCs as shown here. Very important difference. So chemical shift and J coupling constants can be predicted using either semi-empirical method or using DFT calculation. NOE effects can be estimated from the proton-proton distance obtained from calculating molecular geometries. And then what do? You compare your predicted calculated of the experimental with your calculated one, and then that's how do you fit, and then you get your correct structure. However, RDCs cannot be predicted because the alignment tensor is not known a priori. Their application in structural analysis based on a fitting process to select the best fit. The correct structure must be present in the pool of structure to perform the configuration selection. Here is just a diagram of how the fitting is performed. So you get a set of structure, you can use your preferred molecular modeling program to generate your structure, and then they can be read into the software, as Dimitri showed. And then what you do is you provide more than 5 independent values of RDC. Independent means that they are not parallel. Then you calculate an alignment tensor for that particular isomer. Then you back calculate the RDC, you compare, and the best structure is going to give you the best fit. It's going to give you the lowest quality factor, and with the lowest quality factor, you select the correct structure. Here, for example, you can see the molecular formula, experiment for true bond correlation. The structure elucidation generated 146 possible compounds. Then you select by chemical shift, you get the constitution. By DFT, you generate the whole ensemble. Then you measure your RDCs, you fit. SVD fitting gives you the correct configuration of stringing. That's the general procedure to be done. I'm going to show you one example in which you can see a case in which the structure was solved by residual dipolar couplings because J coupling constant and NOE failed to provide a unique solution. This made my colleague Dulcie Mulholland approaching me in a meeting, and then she said that she isolated this compound, got the X-ray from Psilocarpus rumpi, and then but then the plant made this compound in which you have these 2 isomers here, 2 epimers. She acetylated, she separated them, and there is no way to correlate here. It's impossible using NOE. So we align it in the gel, compound 6 and compound 7. We collected RDC for all these carbons. Then we performed the fitting, and then for compound 6, the best quality factor was for the 23R, and for compound 7, the best quality factor was for the 23S, and everybody's happy. So what I just want to say that in order for further reading, RDCs were already featured in the 3rd edition of Tim Claridge's book. In page 371, he featured part of my work. Also, he talked about how promising are the PMMA gels. Now we have more than PMMA. I'm very happy that Tim brought this one to a textbook. I wrote an entry from the Encyclopedia of Spectroscopy and Spectrometry, and about RDCs. Also, we have a book chapter, and also we have a nice chapter, very complete on RDCs on natural products, 55 pages, several compounds, 115 references. Okay, say this, I just want to thanks for your attention. I went over my time. I'm very sorry, but you know, I always complain that I always need more time. Well, thanks again.